on S. So that means we have S applied to E1 equals to kappa 1 E1, and S applied to E2 gives you E2. Where everything should be read like for each point P, we can evaluate both sides. So hence, if you calculate the fundamental matrix of the second fundamental form, so that's where we plug in E1, EI, and EJ in the second form, what we get, which is by definition is just EI times the shape operator applied to EJ. So that's always just like EJ scaled with kappa j again. So it's the diagonal matrix with entries just kappa 1 of P, 0, 0, kappa 2 of P. And moreover, because we know that the connection forms are related to the shape operator, we also see that we can calculate the can calculate these expressions for the omega 1 and omega 2. Essentially, that follows from the equations that we had like last times, just like plugging in now that E1 is like proportional to the S1. So we get the following equations for these connection forms in terms of, because essentially that's like the coordinates are like these, the frames there. Okay, so let's take d of that and see what comes out of these expressions. So take d, like the exterior differential. So what we end up with is that d omega 1 free equals to d kappa 1 which theta 1 plus kappa 1 d theta 1. So that's the statement. And then on S, so we restrict these expressions on S. We can write this one as omega 1, 2, omega 2, 3. And similarly here, we can write it as omega 1, 2, which theta 2, as if you have like these ones and you restrict it to S, you get 0. So we can solve for this expression. So d1 kappa 1 phi 1 if you restrict it to S, then we get something like that is always omega 1, 2 times some wedge product. So we have omega 1, 2. Then we get this term with a minus sign, so that's minus kappa 1 phi 2. And from here we get we get this expression omega 2 3. But from the same, now we can use this expression here to plug this in for the omega 2 3 to provide it as the difference of kappa 2 minus kappa 1 omega 1 2 wedge theta 2. So we would like to actually get an equation for d kappa 1. And in order to do that, we apply E1 and E2 to this equation. So what we get then is that d kappa 1 applied to so then we have like two terms. Like one is like where we have like phi 1 has to eat E1, otherwise it gets 0. So what we end up with that we have like E2 applied, and then we get a minus sign times theta 1 E1, which is 1. And here on the other side, we have kappa 2 minus kappa 1. And now we apply E1 and E2 to these expressions, where we get again omega 1, 2 applied to E1, and then here phi 2 applied to phi 2, and this one is 1. So now we get rid of the minus sign and end up with the following final equation, which is kappa 1 minus kappa 2 omega 1, 2 E1. So that's a formula for calculating the change of the principal curvature in terms of the connection form. And you can do a similar calculation. So here we started with like taking d of this equation, but you can also start by taking d of that equation and doing a very similar formula. And what you end up with then is the following result. The following proposition is that if E1, E2, E3 is a double frame, on S, with connection forms omega ij, then d kappa 1 in E2 direction is given as kappa 1 minus kappa 2 omega 1 2 E1, which is exactly this equation that we just derived. And you get a second very similar equation where we just interchange the wall of 1 and 2. And you get so what are these equations telling you if you look at them? They say that in order to calculate how the principal curvature is changing, or like differently phrased, in order to calculate how to determine how the principal directions are changing, the only thing that you have to know is omega 1, 2. So, and you need all of the information for omega 1, 2, and then you get automatically the change. So there's equivalence. Like omega 1, 2 is, by definition, or by this equation, is measuring the change of the principal curvatures or of the directions. Which is also intuitively clear because in a Darboux frame, E1 and E2 were always in the principal directions. So that means that omega 1, 2, which was the change of E1 in the E2 direction, should be related somehow to how much the principal directions are changing. And these formulas confirm that if you want to calculate the change of kappa, the principal curvatures, then you just like use these equations for a Darboux frame. So that's important that we start with a Darboux frame. And it's this reason why they are like sometimes so important, these Darboux frames, is that because they have like such a nice relationship between the curvatures and okay. So that's essentially all I wanted to tell you related to the normal curvature and like the principal directions that are derived from the normal curvature as the maximum and the minimum. In the following, there's like two different kind of additional curvatures which are very much related to it but are different, and they are called the Gaussian and the mean curvature. So the name Gauss we will like have now quite often. So he was one of the founders of the subject and came up with a lot of these important concepts. So the starting point is another way to extract numbers. From a matrix independent of the basis. So independent of the frame. So suppose we have a T, which is like T1, T12, T12. is a 2 by 2 matrix. I think all of you have seen the determinant in the trace of the matrix. Then the trace, which is denoted by TR of T, we just take the sum of the diagonal elements, and determinant, which is determinant of T, where we take the product of the diagonals minus the product of the off diagonal. And both of them are invariants of T. So they don't depend on the basis. So if you choose a different basis, you might get different entries there, but the determinant and the trace, they don't change under this change of basis. So that's a nice construction that we can do for every 2 by 2 matrix. So now it's very clear what we do. We apply that construction of taking the trace and the determinant to our 2 by 2 matrix that we get from the trace from the shape operator for the second fundamental form. And one remark here is that the determinant we can also write that one as the product of the eigenvalues of T. So if T can be diagonalized, then we can just take the diagonal elements. So these off diagonals are then 0. So we get like that. They are like the eigenvalues. So we now apply the construction to the shape operator. Get the following two important definitions. Just capital K is defined as the determinant of the shape operator of P, and this one is, but this argument that it's the same as the product of the. It's just like the product of the two principal curvatures, because these ones were the eigenvalues of the shape operator. And this one is called Gaussian curvature. And a big capital H, which is just the trace of the shape operator. And by convention, we add a factor of 1/2 over there. And the trace, we can also evaluate it in terms of the basis where we have a nice diagonal expression, and then the trace is just taking the sum of the diagonal entries. So this is the same thing as kappa 1 of P plus kappa 2 of P. And because it's like essentially taking the mean value of these two values, you take like kappa 1 and kappa 2, and you take like what is the middle value between them. This one is called the mean curvature. Okay, so that's just like some definitions. Let's have a look at some examples to get a little bit of a feeling. So first of all, for the plane we have kappa 1 and kappa 2 equals to 0. So in that case, kappa equals 0, and the mean curvature is also 0. Now let's have a look at a cylinder. What is kappa for the cylinder? The big curvature, like what is the Gaussian curvature for the cylinder? Yes, so I heard it already, it's 0, because one of the kappas is 0. Like there's one direction where you always like have no curvature, and then there's like one where you rotate, and that has a. So in this case, we have k equals to 0, but h is not 0. And then another example would be the sphere of radius capital R. And there we have that both of these curvatures are the same, like the principal curvatures are the same, and we get a 1 over R squared as the product of them with a minus sign. With a plus sign. So that's some examples. How is that like related to the discussion that we had earlier? Especially the Gaussian curvature is very much related to elliptic, parabolic, and hyperbolic points. So that's remark. So kappa of P being bigger than 0 equals to 0 or smaller of 0 is equivalent of saying that P is in this case it's elliptic. So these are points where the curvature is like they have to have the same sign. So these are elliptic. 0 would be one of them is 0. So that's parabolic point, as we had like on the cylinder, and smaller than 1 are hyperbolic points. So you see, the Gaussian curvature really makes a allows you to distinguish between elliptic, parabolic, and hyperbolic points. And that example or that remark also shows you immediately what is at least the sign of the Gaussian curvature of the torus, right? Like it shows you like inside, outside, and the both line have like plus, minus, and 0 Gaussian curvature, respectively. So these are like very important invariants. we have the following proposition. Would be the characteristic polynomial, which is given by S of P, is the characteristic polynomial is by definition, if you have an operator, you take S of P minus T times the identity operator, and then you take the determinant. So that's the abstract definition of what is called a characteristic polynomial. It's a polynomial in like T, or maybe I take lambda here. And this one is given by the following expression. And in particular, we get that kappa 1 and kappa 2, the principal curvatures, are given as plus or minus of h squared minus k. So the formulas over here allowed us to define h and kappa in terms of like k and h in terms of kappa 1 and kappa 2. Here we kind of go like the opposite way. It's like once we have h and we have k, we can get back our principal curvatures by this formula. So that's why this formula is sometimes nice. And let's have a look at the proof. So the determinant of S of P minus lambda, the identity, the determinant doesn't change on which kind of basis we choose. We can in particular choose the basis given by the principal directions. So we can in particular choose in this one, we have just kappa 2 so that's the determinant of this operator, and which is nothing than kappa 1 minus lambda, kappa 2 minus lambda, and zeros on the diagonal. So it's just like the product of kappa 1 minus lambda times kappa 2 minus lambda. And now if you expand that, you get immediately this expression once you realize like that is h and there's kappa in there. So that's a nice small remark, but it allows you to, gives you a different way to calculate h and k. So like one way to study that, if you don't know kappa 1 and kappa 2 before, that would allow you, okay, once you have the operator S of P as a matrix, what you do is you calculate this characteristic polynomial, which says like you take like minus lambda and then calculate the determinant. And you get like a certain expression in terms of lambda, and then from that expression you read off the kappa and the h, or you say that it's a trace and the determinant that would be equivalent. And then you could like say like that kappa 1 and kappa 2 are now you can get them out of using this equation. So that's like a different way to at least get like the principal curvatures once you know the shape operator, where you don't have to calculate like necessarily the eigenvalues directly. And the following, there is one more calculation which shows you how to get k and h in terms of the connection forms. And that's the following important proposition. Is like E1, E2, and E3 be a moving frame adapted to our surface, and as before, we have dual frame phi j and connection forms omega I j. And the proposition tells us the following, that if you take d of omega 1, 2 to 1, what we get is our Gaussian curvature phi1 phi 2. So this one is a 1 form, so d is a 2 form. So we have to wedge it to get like a different form. And then the nice part about the Gaussian curvature is that it's related by this formula over the d. And we get a similar formula, or not similar, but we get like a different formula which allows us to calculate h in terms of the connection forms, which is given as 2h. So the last few minutes consist in like proving these equations. So first of all, we call that the second fundamental form, the matrices for these ones, is given by E1. I think this expression we have seen now multiple times, is the matrix expression of the shape operator. So that's like the entries here give us the shape operator, but as a matrix. So the determinant of that expression gives us the Gaussian curvature, and the trace of that gives us equal to k, and the trace of that matrix gives us our mean curvature with a factor of 2. Okay. So now let's start calculating this expression here and see what happens. Maybe I do that on a different blackboard. So So first of all, we have d omega to 1 equals to minus d omega to 1, just to change the indices because it's a bit easier to work with. Now we can use the Cartan structure equation to calculate this expression, and we end up with omega 1 free wedge omega free 2. And now we change again here the index, and then we get rid of the minus sign. So now we need to have these guys, the omega 1 free, and what we are seeing is that these ones are exactly the elements of the matrix. And similarly for the second expression here with the second factor. So if you plug in these expressions, what we end up is so we have these terms, and now we use just like expand all of these expressions and collect these terms that appear. So what we get is this one hits, if it hits like another theta 1 and theta 1 wedge is like 0. So what the only expression get we is theta 1 hitting theta 2. In this case we get the prefactors multiplied, and then we get a second term which has like phi 2 hitting phi 1, but these ones are in a different order, so we get it with a minus sign. So we get the following expression. And here you realize that this one now happens to be the determinant of this matrix times phi 1, phi 2. And as we have seen before, this one is just the Gaussian curvature. So that verifies, hopefully, the first equation here. And the second equation is follows from a similar calculation, namely you start here, and now we insert for omega 1 free, we insert this expression, but then you see the only one that like survives the wedge product with the theta 2 term is this first one. So what we end up here is that it's phi 1 with phi 2, and similarly the only term that survives the wedge product with phi 1 in the second term is given by phi 2, 2. And now you collect these terms and you see that it's 2 times the mean curvature. So what these equations are telling you is like really that these connection forms, if you take the curve, the d of that, that gives you then directly the Gaussian curvature. So that's like a different way to calculate the Gaussian curvature, which doesn't involve at all the shape operator, but just like the connection forms. And you see like the D of the connection gives you the Gaussian curvature. So that's like a very important formula. And then like the mean curvature is related to this omega 1, 2 and omega 2, 3 without any D's. So that's like the gist is that like both K and H can be determined also in terms of the connection forms. Okay, so that's it for today, and then we see each other next week again. Hey. You came to learn some differential geometry?
Yes, and yeah, I went to ask the secretary Qin, and she told me some method of investment, but it seems like this is my answer to you, right?
Okay, yes.
And she told me that on a set,
Yes.
and it seems the part I need don't appear at all.
Okay.
Yeah, it seems I don't have the permission because maybe I'm a student, so maybe I'm gonna apply for more permission.
So that means you don't have the
Yes, and I'll apply for some additional.
Yeah, for me it looks like maybe you can't like what you want.
This one part. Maybe this is second part. Yes.
Okay. But okay, so you will apply for like getting the rights and then.
Yes.
Okay.
Yes, and the bank account you gave me is a salary card.
Yes.
Yes, and it comes to the final page. Like I submit. It need to be a like so-called corporate card.
Yes.
Official card, a business card.
Yes. So that was the problem. I think like last time they also encountered. So apparently I need like a special card or something.
Yes. So,
but I don't know how to get that. So that's
okay. Yeah. You need to fill out another form. Yes. To apply for a corporate card and but this one is totally in Chinese.
Yeah. So the problem was I went with this one to the bank.
No, you just fill this form and give it to the secretary.
Ah, okay, that was the problem. Because like I went to the bank and they said like they don't know what to do with that.
Ah,
okay, good. Okay, good. Okay, so I have to fill out that. Okay.
Yes. And of course I can help you with it, but it seems like there's so many personal information.
Yeah, so I can do that.
Okay.
Yeah. So, okay, good. Yeah, can you just give it to me? Or
Yes.
Okay, good. Is there like something that I need to know what card to select? Or?
Yes, this 801 and just
okay, good.
mark like this.
Okay, so I have to. Okay, good.
I think it's so complicated. There's so many to do.
Yeah, you can't do that digitally. Someone has to type it in.
Like you must write a character like yes, I like this. Yeah, maybe I can help you to
okay, yeah.
write this.
That's about my name or?
No, you sign your name here.
Okay, but this one is about?
Yeah, I can do it. Write it for you now.
Okay.
Like.
You have to draw. Ah.
Yes. Yes. Like this, it seems annoying.
Okay. Yeah, I can do that. I mean, it's nice practice in Chinese.
No, I'll write it for you. Yes. And that's the problem.
Good.
Yes.
But then I will do that and then.
Yes, but of course the biggest problem is that the many invoices over a year.
Yes, yeah. So do you know what to do about that? Or?
I think it's terrible.
Okay.
It's unfortunate, but it seems that we cannot reimburse the things.
Okay. So
and when I try to, and yeah, the system they are not allowed to be uploaded when I try.
Okay. Okay. Good. So I have to somehow ask like the Taobao if they can send me new invoices.
No, they can't send you new invoices because like it's over 1 year.
Okay.
Yes. The school cannot reimburse the invoice over 1 year, and the Taobao they will not give you an invoice after a year.
Okay.
Yeah. It seems the biggest problem.
Okay. Yeah, that's very shitty because it's not like that I forgot to give it someone, but like it's just like yeah, maybe I try it anyway on Taobao. Probably you're right that they just say like that we can't give you a new invoice, but I don't know. Maybe it works.
Maybe I'll ask the secretary again.
Yeah, I mean, like the problem is like, yeah, I don't know. I mean, the problem is that, like, if I would have just forgotten about it, it's like, okay, if they say, like, yeah, sorry, like, it's your fault. But since I gave that, like, to the Shang, okay, I will just ask like on Taobao. Maybe everyone is nice there, and then, but
yeah, like the e-readers, the mouse, even the plant.
Yeah.
The keyboard.
Yeah, okay. I mean, like the biggest one would be the money, right? Like I think that was like 3,000 or something. I think it was quite
Yes, the e-readers 3,158.
yes, and the monitor was also, I think, yeah. So these two things, like if the keyboard is not okay, then okay.
Yeah, and the chair is 1,588.
Yeah.
Yeah, the chair, the lamp, and the mouse. They are all over 1 year.
Yes. Okay. Okay, I will ask. Let's see what happens. If not, then yeah, maybe I also can with Lehman and he shares some idea. Yeah. Okay. Thanks.
Write this down. It's the number. Yeah, and maybe they are writing Chinese.
Do you know how that then works? Like I get now a card which on
Yes.
which I then get money, and how do I get? Then I have to transfer the money to my personal account.
Yeah, when you submit this form and you will get another card.
Okay.
Yes, and that's yeah. So your salary card is a debit card,
Okay.
and this is a credit card.
Ah, okay, good. And I have to have that, right?
Yes.
Okay, good. Good. But I can transfer money then from this credit card to
Yes.
Okay.
So maybe yeah. So maybe you can see this.
No, I trust you there.
Okay.
So, like someone else.
So like